Hello, folks. I don't have slides. That's a good news, right? But I'll have a lot of demo to share, and I kind of have some kind of a deck, but everything created over a terminal. I think I gave a talk a few months before in Command Line Heroes, and that's what I like. How do I do this differently? And that's when I use some open source tools to build it and just reuse it. Let's get started. What are we talking today? We're talking about how Postgres can store all the LLM data that we all use on a day-to-day basis, and how Postgres fits in, how it stores, what are these embeddings. We'll talk about all of those, right? Let's jump in. So this is a overview of like what are the different areas that we'll be covering today. What are embeddings? What are distances? How does a Postgres store the data? And we cannot use B plus trees and B trees, the indexing stuff that folks already talked about in the previous sessions. And if B plus trees are not there, what are other options for Postgres? Some extension that we'll talk about, right? So we'll talk about IVF flat and HNSW. We'll talk at a very high level, and some production tips on how to get this going. Great. So what are embeddings, right? So at the end of the day, like anything that we put on has text, it's just converted as numbers, array of numbers, floating point numbers, right? So in a very simple terms, that's exactly what are embeddings. I think this started, quite some time ago with the word to vector. This existed at least 10 to 12 years before I started coding. And those principles got extended when LLMs were built off, right? So how do I convert all of this text that we as humans understand to some numbers? So, and how computers can make sense out of it. So we'll start from there, very brief one. It's like teaching your database that like if you like something, make an association, right? If car means driving, so those kind of associations can be built up with some mathematical calculations overall. So, okay, let's start with the first demo. I have things already opened up for ease, right? So it's just a bunch of Python scripts and stuff. Like if I would just show even what this even goes inside, right? So just you're seeing what you guys, okay. If what is compare doing at the end of the day? Let me just make it quickly show you that. It's just comparing to some cosine similarities and bunch of things, but yeah, we'll not go into that. That's, just to brief on like what exactly I'm doing. I'm not doing anything fancy, right? So I'm just comparing a couple of things. Let's say I like driving. That's one sentence. And I love cars, maybe, right? So now it's giving me that like both the sentences got converted to a 360, almost 384 dimensions vector. That means that this vector is an array of 384, and it's making a similarity score of 69%, 0.69 is like 69%. If I put exactly the same sentence, right? Something like I like pizza. I love pizza. Almost similar sentence, right? So almost 92% same. So that's both sentences converted to some numbers, and we're making some sense out of it. Just to give a brief of like what is underlying what's happening, it's running something like cosine similarity. We'll come to it what exactly that is, right? So yeah, we compared two different sentences. Now what we're gonna store this to our database. Okay. Now I have another demo that's been running here. What I'm gonna do is the second terminal there. Prices have been increasing lately. Economy is doing not that great. Something like that. Like we will visualize in the database how it's being stored. Now, if I have to query something similar, now since I've added this in the DB, I can call something similar. So now in this, I'll be doing a search operation in the bottom right, where can whatever the information that I fed into the database now, can I pull it in with a semantic search, right? So how do we search in Postgres? We do exact matches, or we do percentage likes, and also there is text search now. But how do I do meaningful searches? So that's where, let me do some similar sentence where what about inflation? If I search, now it got me the top matches. I already tried this before, so I think, yeah, there was some data already. The 86% matches is inflation. The one that we had, prices have been increasing lately. I think that has 35%. It is sorted by like the closest match, right? So with a score 86% to all the way to 35%. So that's what we did now, right? So, and this happened in Postgres. Now let's try to look at the stuff, right? The whatever that we did. I won't bore you with typing each commands. So I have things kept ready so that like we can run the exact scripts, and it's not like I remember all the syntax as well. Okay, this is completely not visible. So I just queried, I did the simple select, ID and content. So this is how my content looks like. Now let's look at the embedding itself. We won't, let's look at only 3 of them so that like we don't, I think I made a mistake copying it. The text, it got overflown. Give me a moment. Let me minimize this a bit so that we can visualize this better. Clear. Okay, that's the stuff. Now we just looked at the array length of the embedding itself. We didn't look at the embedding itself. How those content that we have stored, how it's been converted to. Again, some problem with copying and some formatting issues. Just give me a moment. Okay, so for LO, this is how it's been showing. Like LO has been converted to these 5 numbers, pizza with a typo there, inflation there. So, but this array is much more bigger. We're just like showing the first 5 values. So what we did, we converted simple text to numbers. We stored it in the database. We also tried the matching between how can I do semantic search in Postgres, right? So, and how is this happening? That is where we're going to look next, right? So, and these we call it as dimensions and embeddings. So, and why do we have to convert it to 384 and why not smaller number or a bigger number? Anybody, what is the role of dimensions here? Can it be, instead of 384 length of array, can it be smaller, like 10? Or can it be like more than like 2000 or something? Any answers there? It's more like the way we perceive environment. If it's a 2D, it's not that great. If it's 3D, it's much better. If it's 4D, I would have seen like 6D movies, 9D movies. It's much better experience. Similarly, like the more dimensions, the more data, the more numbers I have, more accurate data is what I get. So that's why the dimensionality matters, where even a simple LO text, if I can expand it to a larger number with storing a lot of information there, giving more information there, that's where it will be much more useful. That's the play about dimensions, right? So yeah, why higher dimensions matter, that was my question there. So let's move on. Yeah, so how does this actually work, right? So all those numbers, I mean, this is something we would have done everybody in school. So we have 2 points in a 2D graph. How do I know the distance? How do I say that, like, is it too far or too near? By calculating the distance between those 2 points. And Pythagoras theorem, that's where that square root of x2 minus x1 whole square plus y2, everybody has done this, right? So as engineers. And similarly, if that can be expanded to higher dimensions, 3, 4, and in our case 384 dimensions, it's a very computationally intensive task. That's how we find the similarity between which text is similar to other text. If it's much more closer, then we say it's similar, right? If it's farther distance, that's when we get a bad number or the distance is quite huge. The same distance formula can be expanded to higher dimensions. That's it pretty much. So we are talking very high level, but yeah, that's the rationality of like how you find similarity between 2 different texts after you convert the numbers. Okay, and talking on that, okay, I hope it's visible. Now we have more than these 3 operators that I have actually mentioned here. but these are the three most popular ones. The first one is a Euclidean distance. That's exactly what we talked about, x2 minus x1 whole square and y2 minus y1 whole square and the square root that you take. That's exactly measuring the distance between two different vectors, different arrays in our case. And the cosine one is more of like, it does not measure the distance, it measures like the angle. This text and the other text, how similar they are. Are they in the same direction or are they in the completely opposite direction? So that the similarity is measured by the cosine distances. And if you have seen that the graphs, right, sine curves and all that stuff, whenever you have an angle delta and all that stuff, that's related to this cosine distance. I mean, we're talking very high level, but the math behind is quite simple that we would have talked about. And the inner product is more of like, it's mostly used for predictions where given this, what else will happen? Or I like this, what else do I like? How do one vector impose a similarity on another vector? That is similarity, like for example, I say I love pizza. With what prediction or with what probability somebody can say that, like how much do I like burger as well, something like that, right? So, and in our case, we'll be using mostly the cosine distance because that's also a question, right? So why do we, in all these three options, for embeddings, there are a lot of GenAI models today. One is, you will see specifically models for text models, you'll see image models, there is embedding models, there are a lot more, right? So we are talking about especially the embeddings. Embeddings is all about like figuring out for this particular text, what else is similar, right? For similarity, the easiest as we say, like it's more of like angle. Okay, am I in the same angle of this particular vector or some other vector? Am I in the same direction of this particular text or something else? So we'll be using cosine distance quite a lot, and that's quite popularly used in embeddings comparison. And where do you use embeddings? It's just mostly to figure out similar text in your RAG applications or where you do fine tuning with some context, right? So mostly around RAG, you will definitely need embeddings, and you'll be choosing some embedding model and whatnot. Cool. Let's do this where I think I've already inserted this data. Inflation is high. What this, we don't have to go into detail of what the script is doing. We are using the cosine similarity. What I'm saying is that like, give me the embedding for this particular content called inflation is high and do the comparison. This is the comparison operator for this embedding with this to get me and the top 5 and limit, do the comparison and limit it by 5 and order by the distance score. That's what we are doing, the top 5, right? So let's do that. For inflation is high, top 5 other related text. And we got that. Zero distance means it's much more closer. So inflation exact match. So other ones that we saw, right? Prices have been increasing lately, blah, blah. So similar stuff that we just saw, right? With the other reinforcing on what we learned. Yeah, we'll talk about this limit part much more. Why is it so much more relevant in this case over the limits that the normal queries that we do where we do without vectors, right? So we'll come to it. Like as of now, just park it for now. Why is it so important? Yeah. Okay. Now we got to know that like Postgres can actually do semantic searches. We can build LLM apps over it. It can convert numbers. It can do matches. But where does Postgres store this data, right? So does it store it like in normal way with all the other tables and stuff? That's something. Let's figure it out. These are some I've already created. I've created this extension. I've already created this doc as well. One thing here to note is that I've created an embedding vector with 1024 dimensions, right? That's quite a big number. And that's a common number as well, 1024 and 1200 something. These are some OpenAI models, and all those models usually use higher dimensions. As we talked about, more dimensions means more accuracy, right? So, and I've also created 50,000 documents just to visualize on what I've done there. I've just used Wikipedia's lot of text, extracted it over. Oh, wait. Let me just quit this just to show. Okay. I've just wrote a Python script, which again I used AI to generate it, where I created 50,000 different text and I've just stored it and I've converted to embeddings, and that's already there in my database. Otherwise, it will take shitloads of time. So to save ourselves that pain. Yeah, we talked about this. Now just let's inspect like what is stored, right? So to get a sense of the data before we proceed on the lot of things. So it has a bunch of text in different languages as well. I've done only top 3. Now it met with positive sales in Japan, and it was like I'm just printing the last 50 characters only. It is much more lengthier, right? So this is what I'm storing. So this is the textful content, and this is also storing the embeddings of each one of them. Okay, that's our base. We'll work on this base itself for the entire rest of the demo that we'll be talking about. Yeah, here is the thing comes in where now it is 1024 dimensions. That means that the array length is 1024, and each of my one array element is taking almost like 4 bytes. Then the entire array itself is taking 1024 bytes. So 4 KB, right? So 1024 into 4 is almost like 4 kilobytes, right? So now let's visualize, let's look at the size of this table itself. I'm just doing this heap size. Very simple query where I'm saying that for the relations called docs, get me the heap size. And heap size does not mean the heap that we talk about in Java or other programming. I'm a dev. No, that's not the heap that we're talking about. The heap is the terminology in the context of Postgres, but it still stores in the disk itself, right? So now if I make this query, it says 12 MB. So where does the data go? So if I have to do a quick math, 50,000 docs into 1024 dimensions into 4 bytes should be 200 MB approximately. Of course, we didn't take care of the content and metadata, blah, blah, right? At least 200 dB should have been there, but we don't see. We see only 12 MB. So that means that these embeddings are not getting stored in the normal way how the tables rows are there. So, and yeah, some GIFs there. Where did the data go? Right? The only heap size is just 11 MBs there, right? It's 11 or 12 MBs. That's where the toast comes in. I think some of you guys who are hardcore into Postgres would have already known this. Anything which is over 2 kilobytes is pushed to toast, something called toast. We'll come to what is toast soon. Just to get a brief of what this does. Now we are looking at the embedding byte size and the entire rows size to get much more clear understanding of what this is happening. Top 3, embedding size is almost 4 KB, row bytes is 4.4 KB, including the content and some metadata and ID, right? So all makes sense. Now there is something called toast. Let's keep it in our mind. We'll explain what is toast. But now what am I doing is that I'm calculating the toast size itself from this table called PG class, which has some information, and I'm calling this rel toast rel ID, which is related to our docs that we created. There is a different table created, which is called toast for our docs table. And let's look at that size, right? So, now it makes sense. Now the data is more. The toast size is, I don't know why did it print twice into 600 MB. Like now we see the missing data. So the data that whatever was supposed to be there, it is getting stored somewhere else called toast. What is that toast? We'll talk about it. So one thing is clear until now, Postgres is not storing the embeddings that we created, the text to those big numbers, not in the normal table that we usually work with, right? So yeah, some calculations there, and yeah. we saw this toast thing. Heap and toast. Can we not have toast at all? Yes, definitely yes. So this toast behavior of storing the information not in the normal table to some other table that's not in the heap to moving it to toast happens only when your row size becomes more than 2 kilobytes. And the page size in Postgres is 8 KB, and where it wants to store, it does not store anything more than 8 KB per page in Postgres. Similarly, Postgres enforces that any particular row, if it goes more than 2 kilobytes, by default, it pushes to something called a toast table. It's more like you have your work desk, you're storing you have laptop, you have some files, and you have some things kept yourself, and you have another storage somewhere where all the other racks are there, right? And every time you you need a file, you have to go there, take that file and come back. That has its own implications, IO reads and bunch of things. I mean, as a general thing, if you can use a lower dimension, that is better. That means that it will store without toast and there's not much IO there, right? So bigger is not always better, at least in this case, right? So what is toast? Toast is the concept in Postgres where it says the oversized attribute storage technique, not the usual toast that we see. It's like, it's a separate storage where every time you need that, you have to get up, which is so annoying. And what that means as programmers or the DBAs or folks who work on the program that we write, what are the different implications that it will have? So that's something that we need to think of. That's the takeaway that's super important. Should I have a bigger dimension? Bigger dimension, more accuracy. What's the trade-off there? More IO, more performance issues and all that stuff, right? So that's a very brief on toast. Now we'll move to the indexing. So one thing we are very clear that like we cannot do B plus trees and B trees, right? So we'll look at the other indexes, right? So first, to get the hang of it, let me just 97 is just random. We can put in any number there, right? So I just get this content with ID 97. This is what the data it's storing. To get the hang of embedding, let me also get the embedding. Embedding is a very huge number, 1024 arrays, right? So let's ignore that. Now for this 97 content, I'm trying to do a comparison of get me top 5 other documents or content which is similar to this Blue Jackets began the year with the worst start in franchise history, blah blah, right? So that's the query, that's what's doing. Maybe you don't have to remember this, right? So if you look at it, got the 5. This is the exact match. It's the same sentence. At the halfway point of the season, the Blue Jackets, I think that's the keyword that is there. Columbus Blue Jackets, I see. Any other things? Franchise history, blah blah, right? So a lot of Blue Jackets and bunch of things around it. Games is there, which is again in the same sentence. It could able to find the similar documents, right? So this, I have not created any index, and this is what we are saying. The problem is that with this is that like since the normal indexing won't work, it's like Postgres is going to search everywhere, like give me this. Since 50,000 is still not a big number, it's still kind of, it's able to get it. But if it was a big number, then it would have really struggled, right? But is it fast? I'm just running an analyze on it. I think we talked about what's the use of analyzing. Samir talked about it and a bunch of others as well. The performance. Now, I think I have the index already, which I created, right? So let me do the drop index. Okay, it's going to execute both, but anyway. It's going to create it again, no? Let me just copy this, no. Clear it off. I'm dropping the index. Oh, it does not exist. Okay. I think there is definitely an index, but it's using a different index. Okay, we dropped a different index. Okay, that's the use of explain query there. Okay, let me drop the right index before we run that. Okay, cool. I'll copy this select statement. Now it's just trying to explain it. It took 195 milliseconds. Let's just keep a note on that, right? So almost like 200 milliseconds for easy to remember, right? So yeah, if you look at the explain statement itself, I think it did a sequential scan, and it looked at 50,000 rows, and they did buffer information and all of that. No, I didn't ask for buffer, so no, that is not there, right? So almost it's storing everything in toast, a lot of IO, right? So let's keep that in mind, and after indexing, how much that would help. But indexing is there, but since the numbers are super huge, what is the easiest way that I can do the indexing here? B plus T, I mean, actually, technically, I mean, theoretically, we can still use B plus T, but the problem is that like it's too many numbers. And for that algorithm, how it's been designed, it's super exponentially, it's going to take shitloads of time to even create index or even to query it. So we cannot do exact matching, exact comparison matching. And B plus tree, as you know, it needs some kind of an ordering, right? 2 is greater than 4, or like, right? So that's how it sorts the numbers and whatnot. And even for text, it sorts by alphabetical orders, and that's how it does things. But in case of vectors, it's a floating point numbers, we cannot do exact matches because it's super costly to do it, right? So we are okay with approximation. If we can do approximation, if we can use some approximation algorithms, then it will be much more faster. And that's where this approximate nearest neighbor algorithms are going to come, and we're going to talk about this a bit, right? So exact does not, I mean, in the case of LLMs or the kind of use case that we have, we don't need to do exact matches, right? So we do some approximation, right? So cool. So what are the options? So as and when the dimensions increase all the way from 2 dimensions to 3 dimensions to 384 to 1024, and some of the dimensions with OpenAI text models embeddings, like I forgot the name, but they usually is 1200 dimensions, right? That means that doing that calculation for such a big number for so many vectors and comparing it, super expensive, right? So and definitely I think, as we talked about, B and B plus T's are gonna struggle. That's where I'm introducing this first indexing strategy called IVF flat. As the name says, it's an inverted file index with flat storage. Flat storage, it does not do any compression like the way it does for normal Postgres data. It stores as in because it has to do calculation, right? Second is that like inverted file. Inverted file is all about like most of you would have worked with Elasticsearch, the TF IDF. It's more of I have to give an example. It's like I want to know in which are the, I mean, usually how do we store the data? Row 1, this document, row 2, this document. That's how we store it in Postgres. But in Elasticsearch, how do we store? Oh, this keyword, this specific keyword, let's say I'm searching for this book. That book itself is going to point to me that, okay, this book is referenced in n number of these kind of documentations. Like, for example, I go to a library and ask, like, can you give me information on economics, macroeconomics? It's going to tell me which are the different books. It has that information. That's what librarian is going to tell me. So that is inverted file indexes, it's a more of inversion of like how do we store data in Postgres. It's based on that, but it's not purely that, right? So let's visualize that with a diagram. With an example. There's a sample doc where this is how we stored the data, right? So there's 6 docs, I say. The cat sat on the mat, dogs are loyal pets, blah, blah, right? Now if I'm searching for this particular query called machine learning algorithms, I have to search one by one sequentially in all of them, right? So that means that I searched all 6 and I found in these 2. Doc 4 and Doc 5 have machine learning, something like that. But again, we talked about this TF IDF in how Elasticsearch stores. Machine learning this is a pre-built index. This is how Elasticsearch works. Machine word is there in Doc 4, Doc 5. Learning is there in Doc 4, Doc 6. Dog is there in Doc 2, Doc 3. That's how it's going to map. And if I'm going to make a query like machine learning algorithms, it's going to look up this table, this index, and it's going to tell, oh, machine learning algorithms are there in Doc 4, Doc 5. This is an inverted way of looking at, right? And this is where the IVF flat comes in. First thing it's going to do is that it's going to convert a data set already to vectors. And second thing, assume that all these points that you see in this GIF is more of those data points, and that is converted to numbers. After that, it's going to do something called clustering. In this case, K means clustering is just a number. In this case, is 3. 3 clusters. It's like dividing the data to, okay, you are all blue shirts, you are all red shirts. These are all formals. These are all your decathlon wear, something like that, right? So that kind of a clustering of grouping the data, it does that. And how this we will use, I think we'll talk about it a bit, right? So yeah, this is the most important one. Let's say these are the clusters that's already been created. This index is already built. Assume that or visualize this is at the index. A new query vector is going to come. And it won't compare with everything. For each of the cluster, there will be something called a centroid, right? And for list 57, this is the centroid. And for list 1, this is the centroid. When the query vector is going to come, it's going to talk to all the centroids. Instead of talking to all the vectors, it's going to just talk to the centroids and find the 2, in this case, top 2. it's going to come, okay, these are the top 2 closest centroids, and it's going to search within this clusters instead of searching everywhere, right? That's a very simplistic view of like IV flat is working. So first, assume that the index is created, query vector is going to come, it's going to compare with all the centroids, which is the nearest centroid, and for a top n, in this case 2, it's going to then go and search only within them. So that's how the indexing works in IVF flat, right? So now let's visualize this very mathematically, right? So in this example, there is only 2 clusters. This is one cluster in the left, one cluster in the right. A is one centroid with that, it's a 2D, that's why we have only 0.15, 0.85, right? So very easy to visualize. And in the second cluster, we have a B point with 0.7 and 0.75 centroid, and even almost the number matches, still it is a little deviated. Let's say a query comes in. This is the query vector, right? The query vector's embedding is 0.72 and 0.85. Visually, if you see, of course, B is closer, right? So then it will just go to B, and then it will search within B itself, the clusters of B. So that's how it works. And if I have to put it very mathematically, first it's going to find the nearest centroids. For machine learning algorithm, it's going to convert it, that embedding, to 2D plane. Let's say it's not possible to convert to 2D, then it doesn't make sense. It's a very big array, very big dimensions. But to make it simplify, if it's assume that if it's just a 2D plane, and this is the embedding for it. The centroids are these 2. It's going to compare the distance. First one is 0.95, second one is 0.003. Then, okay, this is the centroid. It's going to check only within the centroid B's cluster to find the closest other embeddings, right? So visually, that's what happened here as well. So query is much more closer to B, right? So what we did here, we did sequential scanning. That's the classical approach. We understood like how TF-IDF, if you had to use Elasticsearch for this kind of use cases, how much of data it actually comes. Sequential scan, we had to read all the stuff. TF-IDF, we had to check few things instead of doing the entire scan. In IVF flat, it was much more closer, where we didn't check the entire index. We looked at the closest ones and then we went with it, right? So now let's see it in action. I think we understood very theoretical on how this works. I've already created I think we deleted the index now. So let me recreate it. Don't worry about this, what am I doing here? We'll come back to it later, right? So it's gonna be a few seconds for sure. So okay, 2 seconds, not bad. The other index will create, it's gonna take at least 20 seconds. What are we doing here? We're creating an index. So let's analyze like how is the index creation different from the normal tables that we write, right? So I'm using this thing called IVF flat. I'm saying that like create an index of this name on docs using this. I'm passing 2 parameters. As we talked about, for embedding column, use this operation, cosine operation that we talked about. It's look at the angles, right? With list equal to 200. This 200 is more of the 200 clusters. That's what it is, right? 200 different clusters. It's going to create 200 clusters. Any data that you push in, it's going to create 200. For the 50,000 data, it's going to bucket into 200 different clusters. That's what this is doing. We created those. Now we are going to disable the sequential scan because 50,000 is still not a big number. Sometimes Postgres is going to like, oh, this is a small number for me. I'm going to just execute it and try, right? So explicitly, I'm just disabling the sequential scan. And this probe is telling that look at one centroid only. This can be even 10 centroids. That means that in the cluster that we created of 200, don't look for the best, look for the most closest. That's what the probes is saying, IVF flat.probes, right? Now let's do the explain with this being set, right? So I'll look at this execution time, right? So we got a 200 milliseconds, almost 195 something with the normal scan. Now we're getting almost like 3 milliseconds. That's a like super improvement, right? So in the shade buffers, it is 14, disk reads are 2, super good numbers, right? So, and it clearly says that like I use this particular index that we just created. So awesome. Yeah, let's move on. Yeah, some numbers there, right? So IVF this is fast, but definitely that could be better. There are a lot of problems even with this, right? So I will talk about like when to use this to when to use other index. So whenever there is an approximation kind of a problems, you will never have what do you call, straightforward answer, and this exactly what you need to use, right? So whenever we create indexes, we know that, okay, index will use this algorithm. But based on the data, based on the query pattern, we have to decide which kind of index we need to use on different kind of scenarios, right? IVF flat itself, let's say, let me just go back to the diagram that we had, right? So let's say if the my query vector was something closer to here, very close to this, and it was close both to this and this, and there were some data points within this cluster which are much more closer to a better closest approaches. Let's say it selected this. Then there are some scenarios where you might have optimization only for the local minima. You won't have the most optimal solution. And also, since this, we created this for 50,000 docs, and the next, if you have to add more docs to it, then that will become a new cluster. That means that some of those vectors could have been even in this vector. That means that it's not that accurate. So that is one of the problems with IVF flat, right? So, and that's where we talk about the low recall, right? So it needs some tuning, depends on good clustering, and lower recall. Recall is about like the best matches that I get when I make a query. Yeah, this is where we'll talk about something called HNSW. It's a mouthful. Hierarchical Navigable Small World. We'll try to understand what exactly that is. This is the second indexing algorithm that we will use, which is much more better. Think of this like your highways, right? So I drove, I think last 2 months before, all the way from Bangalore to Hyderabad. I took the NH4. There's no deviation all the way from Bangalore to Hyderabad. There is NH44. And then I entered Outer Ring Road. I forgot the ring road's name, Shamshadabad, the exit, and bunch of things. Then I attended a marriage in Gachibowli of my friend, and I had to go through some streets. That's the analogy for this. These are your highways. These are your outer ring roads or main roads or 100 feet or those roads. These are your gullies and streets, right? So how does the algorithm work? To set a base, right? One thing you see is that like highways are few, ORs will be little more, and streets are more, right? So that's the same thing here as well. In each layer, there is a maximum number of connections each node can connect to each other. That is low in here, sparse. It's much more higher in this. It's much more higher in this. And I've taken only 3 layers here. In the actual algorithm, it can be few more layers as well, right? So, and there is something called a current node. So whenever we do a search, it will always search from here for some reason. That's a random number actually, right? And this is our query vector. Algorithm works something like this. This is my query vector and this is my current vector. It's going to check the distance between this. Let's say there is some number. And for this current vector, all the neighbors, there are 2 neighbors for this. One is this, another one is this. Now it's going to check the distance between this and this neighbors. Is it smaller or greater? Definitely the neighbor of this has a smaller distance for this query vector than this. So the current vector becomes this one. Now in this current vector, it's going to check neighbors. It has one neighbor here, another neighbor we just checked. The current distance between this 2 and its neighbors, is it which is shorter? This itself is the shorter. That's when it's going to move to this next level. If there was another vector which was much more closer to query vector than this, then you would have moved there first. It's more of like I take different highways. I first figure out like what is my best next exit, right? So I go as fast as possible in highway, moving to some outer ring roads, right? So then I move down, and the same thing happens even here. It's going to look at neighbors, which is the shortest. There is no shortest, it does not move. If this is the shortest, it's going to just move down to the next level. I've simplified quite a bit here, but there's much more. There's much more layers, and it's much more complex, right? This is something I generated myself to visualize it better. But that's the analogy: highways, so to some outer ring roads, to the gully streets, right? Yeah, so we move from all the way from the top, and we move all the way to the bottom. And here there is no problems like IVF flat, where if you're in a boundary, you might miss something much more better vector than this, right? So higher recall. We'll understand why is a consistent performance. Yeah, we talked about multiple layers there, right? So on the numbers, if people like math, let's say if machine learning algorithm was converted to this 3-dimensional numbers, right, array. Now at the layer 2, let's say I have only 2 docs. And also one thing I forgot to mention, let's say I have 50,000 docs, right? All the 50,000 docs will be here. There will be, let's say, 100 docs here, and let's say less than 10 docs here. So it's like, that's how it's created. There will be duplicates in each layer, similar docs converted as vectors and vector points, right? So in our example, that math example that we talk about, layer 2, let's say there are only 2 docs and they are linked to each other. And the query vector's distance from doc 4 is 0.02 and doc 5 is 0.04, which is farther. It's going to stay at doc 4. That's what we talked about. And we'll move to the layer 2 to layer 1. In this, doc 1 and doc 3 are connected. So total we have only 6 docs. In this, apart from doc 2, everything is there. Doc 4, doc 5, doc 6 are connected. And the distance from the query vector is 0.02 for this. And for others, it's much more higher. So it's going to stay again in the doc 4. And just to visualize, that's how it's going to move, right? Expressway to main roads to this, right? From bottom to top. But I've simplified quite a bit. It's like GPS navigation in a way, right? So now we saw 4 things. Sequential scan. Let's say I have to find an analogy of, I'm looking for an Italian restaurant to have some thin crust, some stuff, right? So I want to eat some pasta or something. In sequential scan, I'm going to go each restaurant. I'm going to ask, do you have Italian? Do you have Italian? TF, IDF is like, okay, I have a list of addresses where there's Italian, so I can directly jump on it. IVF flat is more like, first I take a place where the written restaurants first, then I go like which one I want to go, right? So that's more of figuring out the overall centroid or the cluster first. And HNSW, hierarchical, navigable, small word, mouthful, is more about like, oh, I know exactly where I want to go. I put the Google Maps and I want to just drive there, right? So that's more of this HNSW, the analogies that we want to keep on, right? Yeah.
Can you control the number of layers you have?
No, unfortunately. Yeah, it's done within the algorithm. Yeah, good question. Yeah, right. So I recall more consistent performance. I didn't explain exactly why, but since things don't move, so you get much better number of times you call. The way it's designed is that you get same consistent numbers or same consistent similarity. Unlike some LLMs, you ask the same thing, it will give some other answers different times, right? That does not happen with this, is what they claim. I didn't talk about why though, but even I don't know why, but yeah. Cool. Let's see it in action. How was the performance? So we're going to drop the old index which we created with IVF flat. We're going to create this one. This takes a little more time. That's the drawback, right? So now if you observe, this is going to take at least 20 seconds compared to IVF flat. So now you can draw the comparison, right? If you want a quicker index to be created every time, use IVF flat. You can to trade off for slower index creation. That means that you can use HNSW, which is much more efficient and much more, not efficient, but it is much more accurate, right? So almost it took 20 seconds, right? So you can see the trade-offs, different things we might have used in different scenarios. So for read-heavy workloads, I might use HNSW. For write-heavy thing, I don't want to use this because it will slow down my writes, right? So now let's look at this. What is it saying? Let's understand this index creation itself. It was similar to other one, IVF flat. What we are saying is that use cosine ops for embedding. That's something we already saw. MS16. This 16 means that the maximum number of connections that one node can connect to other nodes. That is this number. And EF construction 200 is that always, let's say I'm connecting one node A. I want to figure out where should this node A should get connected. What am I saying with EF underscore construction is that connect with the best 200 of them. I have a lot of options. Keep a bucket or a heap of top 200 and connect to only them. That's what it's doing. Just to understand what's happening there, right? So now let's do the search. We created the index. And this EF search, I mean, too many terms. EF search equal to 40 is saying that give me, while am I searching, give me the top 40, right? So that's what it's keep a bucket of top 40, and limit is saying like, give me that, after you do that, give me the top 5 out of that, right? So, and you can set it to 100 as well, where you see that like it will create a bucket list of 100. If it finds a better answer, it's going to kick out something else and it's going to put something back in. So that is what EF search is doing, like top best, something like that, right? So, oh, it took 9 milliseconds. That's quite a lot, to be honest. Oh, 3, yeah. If we run multiple times, it's taking anywhere between 5 seconds and whatnot, right? So you can see the contrast, almost 2 milliseconds. And buffers read at 1. It used this particular index. Yeah, pretty cool, to be honest, right? So, and it looked at the shade buffers itself. Yeah, it does not have any reads, that it didn't read anything from the disk. That's 0, right? So it read everything from the index. Awesome. So this is the difference or trade-off that you see, speed versus accuracy, when to use what, right? So let's move on. Just a comparison on how these things work. Just put up a number. I think we want to spend time on this. Yeah, we talked about this limit, right? This is super important. Unlike the limit that we see in the normal queries in databases, where you do everything and just give me the top 5, right? So in case whenever you have enabled vectors and you're doing this kind of a similarity searches, if you don't use limit at all, it does not even know that you have to it has to use indexes. That's one problem. And the behavior is inconsistent as well. Maybe in the later versions that they would have fixed this, but at least it's not being fixed. So limit is super important, right? So limit will help you to force that you have to use ANN, the approximate nearest neighbor algorithms. That can be IVF flat or HNSW, whatever is there, and it's going to give you the best top En. That is the n in the limit, right? So limit is much more important here. With a query without a limit here is very expensive. It might do sequential scan, right? So cool. Sorry. Let's talk about production challenges, given that we talked about indexes, 2 different indexes, right? So I think MVCC, I think most of you guys know. I mean, you guys work on Postgres day-to-day basis. MVCC is a school thing that was introduced by Postgres later, I think after 7, if I'm not wrong, where like other databases which locks the entire row that has a contention for reads. Postgres creates this multi versions of each row so that like your reads are not blocked and still you're consistent, right? So where each row is maintaining a particular versions when there is an update, so that like if there are multiple reads and writes at the simultaneously, like it gives a consistent non-blocking way of dealing things. That's something you will have seen. In our case, whenever we have indexes, since each row will make a copy of other rows because version is maintained. In our case of dimensions, which is like 1024, big number, it's not like a single column or a single field within a cell within a database. That means that every update that you do, it's going to like do a copy of the entire thing, and you're like increasing the space. That means that you need to be a little more cognizant about like now which index to use, or should I have much more buffer in my database so that like I don't get into issues of the no space left in device kind of errors and all that stuff. We talked about like 50k rows here, and I think if we run some experiments, it will be like few MBs. Think about if it's a few million rows, then this bloat of MVCC where it will create another copy in another toast, it's going to go into GBs, right? So that's something to be keeping in mind while we run this production workloads for these kind of systems, right? So whenever you see vectors and these LLMs, there is always a trade-off. It's not straightforward at all. Like it's much one level upper than the distributed systems and the trade-offs that we deal with, right? Okay, with that being said, like what can we do, right? So what's the solution for it? So one of the ways, I mean, it's not a like foolproof solution. At least if I can, what am I doing is that I'm separating my tables into 2 different things. In one, I'm just storing the actual documents, title, content, and metadata. In the other table, I'm just doing a reference. I've created the embeddings. I'm creating a reference for the document itself. The benefit of this is that whenever I update the metadata, now the entire row does not have to be pushed, right? So now this is in a different table altogether. So if I modify metadata, it does not affect my embedding, right? So entire toast have to be, toast issues and going into another table and like looking up where my shirt is, or where my file is, those issues are something we can avoid, right? Couple of other tips. What about the embedding? So this is more of like when to use what. I don't know if the text is too small. If there are no requirement that you need too much accuracy, I think you can just use smaller dimensions, smaller vectors. But the trade-off here is at accuracy, but that means that you have better I/O. That means it's some workloads where you have to do simple things and you don't have to deal with accuracy. Sure, you can use smaller arrays so that a toast problem does not come up. And this maintenance work memory, this is something to create indexes, and since a large number, this memory needs to be high and this space needs to be given. Otherwise, you'll end up issues where it cannot even create an index. There's a lot of calculations are happening, and it puts into this memory multiple times so that it can do the effective calculations in a period. So I think Shamir also talked about analyze. Specifically in the vector case, it's much more important because if you don't even run that, so analysis of the docs are important, which will be used by the index. Should I even use the index, or what kind of index should I use? If you don't even run this, that information is not available. That means that whenever you run queries, it might not even use your indexes. It might end up with sequential scans, right? So, and the second thing, right? Create indexes after bulk loading. This is a very quirky thing. It's more of if we create the index and then load the data, that means that it's much more slower from the experiment, like where it has to change every time. It's going to change the index, it's going to commit, it's going to change the index, it's going to commit. But in the case of IVF flat, it is much more optimized, where if you write the data and do the index creation later, it's much more faster. It's a one-shot operation where it can skip a lot of other metadata works, which it has to do for every data operations, right? So in case of IVF flat, try to do it in a bulk as much as possible. That's the recommendation there. Right. So I think this is the last. And the limits, I think we already talked about it. So difference between limits and normal sequels to vectors, how does it differ? And why is it specifically important in this, right? So otherwise it's going to read the entire scan, right? So unfortunately, that's how it's been designed. And when to use what? Partially we talked about it, where read or AV operations go with HNSW. For something where write AV, go with IVF flat, because index creation itself takes a lot of time in HNSW, right? So, and some production examples where in what to use where I've just listed down there, right? So, and should we use pgvector, right? So one thing in the first place, not every time. So you need to be specific, you need to be clear on like, what is the use case here? Do you want to make an exact keywords? Then just use a FTS that's already available. If the number of docs itself is less, you're just over-optimizing. Over-optimization is the root of all evil. That's something we have all heard multiple times in our life. So you don't even need all this fancy indexes if the number of documents are less, right? So, and it generally, there's no, I don't have anything to back on this number, but it's like a general rule of thumb, or where if you need better features and if the vectors numbers are super high, it's better to go with specialized vector databases rather than using Postgres itself. But in most of our workloads where we cannot change the database and we still want that feature, at least some of them on the basic stuff, I think Postgres is killing it, to be honest, right? So yeah, the biggest takeaway is that, like, yeah, we can use Postgres to do the best things it can already do, like it do assets, it does SQL on existing infrastructure. With that, we can also do semantic searches. That means that we can build LLM apps based out of it, using the open source stack completely, right, without breaking a sweat. So, and today we cover about like where does the data get stored when we do the indexing, or even where does the embedding data itself is stored, what are the different strategies of doing indexing, and some production gotchas, right? There are definitely much more, but I just try to touch on the most obvious or important ones today. Yeah, that's it. End from me. Thank you, folks. Hope you all learned something, one or two stuff to take away. Yeah, the slides is just a markdown file if you want to get it, and code is there. It's all open source. I put it up in GitHub. Yeah, that's it. I don't know if you guys have questions. I hope not. But yeah, oh, there's a question. Yeah.
Let's say that I have a multi-terabyte invented tool which I have created.
Multi-terabytes don't use. Yeah.
Because we have worked in the bank as a program, so we have the figures like query, let's say that. But when I do that, I have to make the query node failure.
What, node failure? Yeah. Don't use it for big data. I told you.
Because you're talking about regarding to the on-premises, not with the cloud.
Yeah. That's much more painful. Don't do it.
Because we actually do it. There
Yeah.
is no internet sources regarding to the client.
Yeah. Understandable. Yeah.
Any latencies? That's what
Definitely there. Yeah. So and also today there are a lot of open source databases of a specialist for vectors. So that's super cool. And Redis, I mean, that also is easy to host and it can do semantic caching on top of it.
Salesforce products with regard to the PostgreSQL, because I sat like close to 7 to 8 hours with regarding to the retrieving all the pages with regard to data. Yesterday, not with the bigger picture,
Yeah.
the last night. That's what I was asking.
Yeah. Good stuff. Definitely this might be solved in the future, but today it's not there, I think. Every database wants to be everything today. MongoDB wants everything, and I don't know. Everybody's like copying everybody else. It's like even Java and programming languages also did the same thing. JavaScript had event loop. Oh, Java's like, we are missing out, we'll add it. JavaScript was like, Java has classes, we don't have classes, let's add it, right? So all the versions, I mean, everybody wants to be everything today. And for most use cases, a single language or single tool works, but for specialized works where it's much more optimized, I think we need to pick the right tool for the right job. That's my argument to that. Yeah. And thank you. I hope no question there. Thanks.